Hello, welcome to this lecture. Here it's a quick revision on charges and fields, electrostatics class 12. I have got list of formulas here. We will be going through each formula and finding out what exactly the formula is. Starting from the charge, any amount of charge can be represented in terms of the basic charge, that is charge of electron 1.6 into 10 to the power minus 19 coulomb, where n is just integral multiple, and here it is a total charge integral multiple of basic unit charge. Depending on how charge is distributed, we have defined three factors. One is called linear charge density, surface charge density, as well as the volume charge density. So, linear charge density is dq by dl and the charge per unit length. Surface charge density is charge per unit area. Volume charge density is charge per unit volume. For the continuous distribution of the charges, the total charge can be found by integrating the linear charge density with respect to the whole distribution length. If it is a case of a surface, then it is integral of sigma dA. If it is a distribution of charges around the volume, it is just total charge is just equal to integral of rho dV, where rho is the volume charge density. Suppose you've got two charges separated by a distance r. The force of attraction or repulsion, depending on the nature of charge, the magnitude of the force is given by 1 by 4 pi epsilon naught q1 q2 by r square. This force is directly proportional to amount of charges separated, and also it is inversely proportional to square of the distance between them. We can define what is the electric field at any point. This is a charge q. At this point, at the distance r, if you want to know what is the electric field, the form, it is found by calculating what is the force experienced by any test charge. That is just 1 by 4 pi epsilon naught this charge into test charge dividing by square of the distance by using this. The force per the test charge will give you what is the electric field at any given point. So, it is equal to 1 by 4 pi epsilon naught q by r square. So, direction of electric field is always in the direction of the electrostatic force experienced by that test charge. If there are two charges separated, equal charges, it may be equal or anyway equal nature, same nature, two positive charges or two negative charges. The neutral point exists in which the total electric field due to these two charges is 0. So, for example, it exists at this point in between the line joining two charges. R is a distance between two charges. Let me say x is a distance from the charge q1 to the point where the total electric field is 0. So, this is x and this will be r minus x. So, electric field due to this charge is 1 by 4 pi epsilon naught q1 by x square. Electric field due to this charge is 1 by 4 pi epsilon naught q2 by r minus x whole square. At this point, both the electric fields remain same. That is why it is equal to q1 by x square is equal to q2 by r minus x whole square. Coming to the dipole moment, if there are two charges, equal charges, one is minus q, another one is plus q, separated by certain distance, finite distance, we call it as 2a, then we can define what is a dipole moment. Dipole moment is just equal to product of any charge. It is actually equal. So, the magnitude of a charge q and dipole distance 2a. So, that is called dipole moment. When can we say that it is a short dipole? This is the center of the dipole and this is a, and here it is a, totally that is a 2a. Or along the axial line, this is axial line. Suppose r is a distance from the center to the point P in which I want to find out what is the electric field. If this distance r is very much greater than this dipole length or a, so the point in which you want to find out what is the electric field is very, very far away from the dipole, then we can call this dipole as a short dipole. For that case, the electric field at any point for the distance r is just given by 1 by 4 pi epsilon 2 pi by r cube, where p is the dipole moment. If it is a case of equatorial line, for example, this is a case, equatorial line, at the distance r from the center, the electric field, if you want to find it for the short dipole, it is given by 1 by 4 pi epsilon naught P by R cube. And electric field varies inversely with the cube of distance if it is a case of a dipole, as well as for the axial and equatorial. If you have got a dipole, if it is placed in external uniform electric field, then there is a rotational effect of force, and it's a torque which is a vector quantity which is given by cross product of dipole moment and electric field, which is nothing but P E sin theta n cap, and direction of torque is always perpendicular to the plane containing the dipole moment and electric field. We define one thing, we call it as the electric flux to measure number of electric field lines, and it is just equal to dot product of electric field and the area. It is just a scalar, it will give you a number. You take dot product of two vectors, it will give you a scalar which is a flux, and it is E A cos theta. The number flux, the amount of lines or the number of lines depends on the angle theta, that is angle between electric field and the area. If the charge is distributed continuously for the on the surface, then the total flux is equal to integral of E dA. You have to integrate with respect to area. Gauss law says the total electric flux in the enclosed surface, actually the surface will be closed with the charges, is equal to summation q by epsilon naught, or 1 by epsilon naught times the total charges enclosed in the surface. Phi is just integral of EdA, which is equal to summation q by epsilon naught, which is one of the Maxwell's equations. The applications of this Gauss law says the total flux is just equal to 1 by epsilon naught times the total charge enclosed. If it is a case of the sphere with a uniform distribution of charge, here all the charges are distributed at a distance r from the center, that means the radius of the spherical charged sphere is r. Then you can find out what is the electric field inside the sphere, on the surface of the sphere, and as well as outside the sphere by using the Gauss's law. And it is found that inside the sphere the electric field is equal to 0. On the surface of sphere for the radius r, the electric field is 1 by 4 pi epsilon naught q by r square. It is a maximum. The value of electric field intensity is maximum on the surface of the charged spherical shell, and as you go away from the surface, it just decreases inversely with the square of the distance. If it is a case of a very straight long wire, infinitely long wire, uniform distribution of charges, if you want to know what is the electric field at the point P at a distance r from the wire, you can make use of a Gauss law and get the equation for electric field, which is given by lambda by 2 pi epsilon naught into r. Again, E is inversely proportional to r. As you go away from the charged conductor, you will have less values of electric field. If it is a case of a very plain sheet, infinitely plain sheet, I say uniform distribution of charges as well. If you want to know what is the electric field at this point at some distance r, it is just equal to sigma by 2 pi epsilon naught, sigma by 2 epsilon naught, where sigma is surface charge density for this plane sheet. Epsilon naught is electric permittivity of vacuum of free space. If it is a case of between two parallel plates, infinite thin plates, the electric field in between two parallel plates is just equal to sigma by epsilon naught. Just you have to add up these two, this sigma by 2 epsilon naught 2 times. If the charge is accelerated in an electric field, if it is uniform, then whatever the work you do in accelerating charge is just equal to kinetic energy. The work done is just equal to q into the potential difference you maintain to accelerate the charge. That is qv is equal to half m square. This v is the speed, this v is the potential difference maintained. So if you want to know what is the speed of the electron or any charge particle, v is equal to, you can just solve this square root of 2 qv by m. So if you increase the potential difference, this speed also increases. If the body if the body has got some charge, if it is accelerated with certain speed v, the force acting on the body is just m into a, which will be provided by the electrostatic force, which is given by the charge into electric field. If it is electron, it is charge of electron. If it is a general thing, general particle, it could be the charge of that particle. So that A is acceleration, which is equal to E by m, which is given by acceleration of the charged particle. Thank you for watching this.